Learning objectives. In this chapter, the user would learn the following in detail. Review of ALOHS and CSMA. Stability in slotted ALOHA, pseudo-Bayesian algorithm, splitting algorithms, tree and first come first serve, FCFS splitting. Review of ALOHA and CSMA. Slotted multi-axis and the ALOHA system. Satellite channels, multi-drop telephone lines, and multi-tap bus systems all share the feature of a set of nodes sharing a communication channel. If two or more nodes transmit simultaneously, the reception is garbled, and if none transmit, the channel is unused. The problem is somehow to coordinate the use of the channel so that exactly one node is transmitting for an appreciable fraction of time. Slotted Aloha. The Aloha network was developed around 1970 to provide radio communication between the central computer and various data terminals at the campuses of the University of Hawaii. This is an improvement of the unslotted Aloha. The basic idea of this algorithm is that each unbacklogged node simply transmits a newly arriving packet in the first slot after the packet arrival, thus risking occasional collisions but achieving very small delay if collisions are rare. This approach should be contrasted with TDM, in which, with M nodes, an arriving packet would have to wait for an average of M/2 slots for its turn to transmit. Thus, slotted Aloha transmits packets almost immediately with occasional collisions, as TDM avoids collisions at the expense of large delays. When a collision occurs in slotted Aloha, each node sending one of the collision packets discovers the collision at the end of the slot and becomes backlogged. If each backlogged node were simply to retransmit in the next slot after being involved in a collision, then another collision would surely occur. Instead, such nodes wait for a random number of slots before retransmitting. To gain some initial intuitive understanding of slotted Aloha, we start with an instructive but flawed analysis. With the infinite node assumption, that is 6b, the number of new arrivals transmitted in a slot is a Poisson random variable parameter lambda. If the retransmissions from the backlogged nodes are sufficiently randomized, it is plausible to approximate the total number of retransmissions and new transmissions in a given slot as a Poisson random variable with some parameter g greater than lambda. With this approximation, the probability of a successful transmission in a slot is g e power minus g. Finally, in equilibrium, the arrival rate lambda to the system should be the same as the departure rate g e power minus g. This relationship is illustrated in the figure below. The maximum possible departure rate, according to the previous argument, occurs at g is equal to 1 and is 1 by e, approximately equal to 0.368. For any arrival rate less than 1 by e, there are two values of g for which the arrival rate equals the departure rate. The problem with this elementary approach is that it provides no insight into the dynamics of the system. As the number of backlogged packets changes, the parameter g will change. This leads to a feedback effect, generating further changes in the number of backlogged packets. To understand these dynamics, we will have to analyze the system somewhat more carefully. The simple picture below, however, correctly identifies the maximum throughput rate of slotted aloha as 1 by E and also shows that G, the mean number of attempted transmissions per slot, should be of the order of 1 to achieve a throughput close to 1 by E. If G less than 1, too many idle slots are generated, and if G greater than 1, too many collisions are generated. To construct a more precise model, assume that each backlog node retransmits with some fixed probability QR in each successive slot until a successful transmission occurs. In other words, the number of slots from a collision until a given node involved in the collision retransmits is a geometric random variable having value I greater than or equal to 1 with probability QR into 1 minus QR the whole power I minus 1. The original version of slotted aloha employed a uniform distribution for retransmission, but this is more difficult to analyze and has no identifiable advantages over the geometric distribution. The behavior of slotted aloha can now be described as a discrete time Markov chain. Let n be the number of backlog nodes at the beginning of a given slot. Each of these nodes will transmit a packet in the given slot independently of each other with probability QR. Each of the m-n other nodes will transmit a packet in the given slot if one or more such packets arrived during the previous slot. Since such arrivals are Poisson distributed with means lambda by m, the probability of no arrivals is e power minus lambda by m. Thus, the probability that an unbacklogged node transmits a packet in the given slot is QA is equal to 1 minus e power minus lambda by m. Let QA of I, n be the probability that I unbacklogged nodes transmit packets in a given slot, and let QR of I, n be the probability that I backlogged nodes transmit. QA of I, n is equal to m minus n I into 1 minus QA power m minus n minus I into QA power I. QR of I, n is equal to n I into 1 minus QR the whole power n minus I into QR power I. Note that from one slot to the next, the state, that is, the number of backlogged packets, increases by the number of new arrivals transmitted by unbacklogged nodes less 1 if a packet is transmitted successfully. A packet is transmitted successfully, however, only if one new arrival and no backlogged packets or no new arrival and one backlogged packet is transmitted. Thus, the state transition probability of going from state n to n plus I is given by Pn, n plus I is equal to QA of I, n when 2 less than or equal to I less than or equal to m minus n. QA of 1, n into 1 minus QR of 0, n when I is equal to 1. QA of 1, n into QR of 0, n minus of QA of 0, n into 1 minus QR 1, n if I is equal to 0. QA of 0, n into QR of 1, n when I is equal to minus 1. Figure illustrates this Markov chain shown in this screen. The state can decrease by at most 1 in a single transition and this makes it easy to calculate the steady-state probabilities iteratively, finding Pn for each successfully larger n in terms of P0, and finally finding P0 as a normalizing constant. From this, the expected number of backlogged nodes can be found, and from Little's theorem, the average delay can be calculated. Unfortunately, this system has some very strange properties for a large number of nodes, and the steady-state results seen are very misleading. To get some intuitive understanding of this, note that we would like to choose the retransmission probability QR to be moderately large so as to avoid large delays after collisions. If the arrival rate is small and not many packets are involved in collisions, this works well and retransmissions are normally successful. On the other hand, if the system is afflicted with a run of bad luck and the number of backlogged packets n gets large enough to satisfy QRn greater than 1, then collisions occur in almost all successive slots and the system remains heavily backlogged for a long time. To understand this phenomenon quantitatively, define the drift in state n dn as the expected change in backlog over one slotted time starting in state n. Thus, dn is the expected number of new arrivals accepted into the system, that is m minus n of q0, less than the expected number of successful transmissions in the slot. The expected number of successful transmissions is just the probability of a successful transmission defined as P success. Thus, dn is equal to m minus n into qa minus of P success, where P success is equal to qa of 1, n into qr of 0, n plus qa of 0, n into qr of 1, n. Define the attempt rate g of n as the expected number of attempted transmissions in a slot when the system is in a state n, that is g of n is equal to m minus n into qa plus nqr. If qa and qr are small, P success is closely approximated as the following function of the attempt rate. P success is approximated to g of n into e power minus of g of n. This approximation can be derived directly from the equation for P success using the approximation 1 minus x the whole power y is approximated to e power minus xy for small x in the expressions for qa and qr. Similarly, the probability of an idle slot is approximately e power minus g of n. Thus, the number of packets in a slot is well approximated as a Poisson random variable, but the parameter g of n varies with state. Figure illustrates the equations for the case qr greater than qa. The drift is the difference between the curve and straight line. Since the drift is the expected change in the state for one slot to the next, the system, although perhaps fluctuating, tends to move in the direction of the drift and consequently tends to cluster around the two stable points with rare excursions between the two. There are two important conclusions from this figure. First, the departure rate, that is P success, is at most 1 by E for large M. Second, the departure rate is almost zero for a long period whenever the system jumps to the undesirable stable point. Consider the effect of changing QR. As QR is increased, the delay is retransmitting a colloided packet decreases, but also the linear relationship between n and the atom rates g of n is equal to m minus n into qn plus nqr changes, that is, g of n increases with n faster when qr is increased. If the horizontal scale for n is held fixed in figure, this change in atom rate corresponds to a contraction of the horizontal g of n scale and thus to a horizontal contraction of the curve g e power minus g. This means that the number of backlogged packets required to exceed the unstable equilibrium point decreases. Alternatively, if QR is decreased, retransmission delay increases, but it becomes more difficult to exceed the unstable point. If QR is decreased enough while still larger than QA, the curve g e power minus g will expand enough in figure that only one stable state will remain. At this stable point, and similarly when QR is equal to QA, the backlog is an appreciable fraction of m, and this means both that an appreciable number of arriving packets are discarded and that the delay is excessively large. The question of what values of QR and arrival rate lead to stable behavior, particularly when QR and arrival rate vary from node to node and infinite buffering is provided at each node, has received considerable theoretical attention. These theoretical studies generally assume that nodes are considered backlogged immediately on arrival. If QR is small enough for stable operation, then the delay is considerably greater than that with TDM. Thus, these approaches are not of great practical importance. If we replace the no buffering assumptions with the infinite node assumption, the atom rate g of n becomes lambda plus nqr, and the straight line representing arrivals in figure becomes horizontal. In this case, the undesirable stable point disappears, and once the state of the system passes the unstable equilibrium, it tends to increase without bound. In this case, the corresponding infinite state Markov chain has no steady state distribution, and the expected backlog increases without bound as the system continues to run. From a practical standpoint, if the arrival rate lambda is very much smaller than 1 by E, and if QR is moderate, then the system could be expected to remain in the desired stable state for very long periods. In the unlikely event of a move to the undesired stable point, the system could be restarted with backlogged packets lost. Unslotted Aloha. Unslotted or pure Aloha was the precursor to the slotted Aloha. In this strategy, each node, upon receiving a new packet, transmits it immediately rather than waiting for a slot boundary. Slots play no role in pure Aloha, so we temporarily omit the slotted system assumption. If a packet is involved in a collision, it is retransmitted for a random delay. Assume that if the transmission times for two packets overlap at all, the CRCs on those packets will fail and retransmission will be required. We assume that the receiver rebroadcasts the composite received signal, or that all nodes receive the composite signal, so that each node, after a given propagation delay, can determine whether or not its transmitted packets were correctly received. Following figure shows that if one packet starts transmission at time t and all packets have unit length, then Any other transmission starting between t-1 and t+1 will cause a collision. For simplicity, assume an infinite number of nodes and let n be the number of backlogged nodes at a given time. For our present purposes, a node is considered backlogged from the time it has determined that its previously transmitted packet was involved in a collision until the time that it attempts retransmission. Assume that the period until attempted retransmission t is an exponentially distributed random variable with probability density x e power minus xz, where x is an arbitrary parameter interpreted as a node's retransmission attempt rate. Thus, with an overall Poisson arrival rate of lambda to the system, the initiation times of attempted transmissions is a time-varying Poisson process of rate g of n is equal to lambda plus nx, in which n is the backlog at a given time. New arrivals, retransmission. Consider the sequence of successive transmission attempts on the channel. For given I, let Ti be the duration of the interval between the initiations of the ith and I+1th transmission attempt. The ith attempt will be successful if both Ti and Ti-1 exceed 1, assuming unit length packets. Given the backlog in each intertransmission interval, these intervals are independent. Thus, assuming a backlog of n for each interval, we have P success is equal to e power minus 2 gm. Since attempted transmissions occur at rate g of n, the throughput, that is, the expected number of successful transmissions per unit time, as a function of n, is throughput n is equal to g of n e power minus 2 gn. Figure illustrates this result. The situation is very simple to that of slotted aloha, except that the throughput has a maximum of 1 by 2e achieved when g to half. The analysis above is approximate in the sense that equation seen for P success assumes that backlog is the same in the interval surrounding a given transmission attempt, whereas according to our definition of backlog, the backlog decreases by 1 whenever a backlogged packet indicates transmission and increases by 1 whenever a collided packet is detected. For small x, that is, large mean time before attempted retransmission, this effect is relatively small. It can be seen from figure that pure aloha has the same type of stability problem as slotted aloha. From the limited feedback assumed here, stability is quite difficult to achieve or analyze, as is the case with slotted aloha. Very little is known about stabilization for pure aloha, but if A is very small and the mean retransmission time very large, the system can be expected to run for long periods without major backlog buildup. One of the major advantages of pure aloha is that it can be used with variable length packets, whereas with slotted aloha, long packets must be broken up to fit into slots and short packets must be padded out to fill up slots. This compensates for some of the inherent throughput losses of pure aloha and gives it an advantage in simplicity. Carrier sensing. In many multi-access systems such as local area networks, a node can hear whether other nodes are transmitting after a very small propagation and detection delay relative to a packet transmission time. The detection delay is the time required for a physical receiver to determine whether or not some other node is currently transmitting. This delay differs somewhat from the delay, first, in detecting the beginning of a new transmission, second, in synchronizing on the reception of a new transmission, and third, in detecting the end of an old transmission. We ignore these and other subtleties of the physical layer in what follows and simply regard the medium as an intermittent synchronous multi-axis bit pipe on which idle periods can be distinguished with delay from packet transmission periods. If nodes can detect idle periods quickly, it is reasonable to terminate idle periods quickly and to allow nodes to initiate packet transmissions after such idle detections. This type of strategy, called Carrier Sense Multi-Axis (CSMA), does not necessarily imply that the use of a carrier but simply the ability to detect idle periods quickly. Let beta be the propagation and detection delay in packet transmission units required for all sources to detect an idle channel after transmission ends. Thus, if t is the time in seconds, c is the raw channel bit rate, and L is the expected number of bits in a data packet, then beta is equal to Tc by L. The performance of CSMA degrades with increasing beta and thus also degrades with increasing channel rate with increasing packet size. Consider a slotted system in which if nothing is being transmitted in a slot, the slot terminates after beta time units and a new slot begins. This assumption of dividing idle time periods into slots of length beta is not realistic, but it provides a simple model with good insight. We have thus eliminated our previous assumptions that time is slotted into equal duration slots. We also eliminate our assumption that all data packets are of equal length, although we still assume a time normalization in which the expected packet transmission time is 1. In place of the instantaneous feedback assumption, we assume 0, 1 E feedback with a maximum delay beta. For simplicity, we continue to assume an infinite set of nodes and Poisson arrivals of overall intensity lambda. We first modify slotted aloha for this new situation, then consider unslotted systems, and finally consider the FCFS splitting algorithm. Splitting algorithms. Slotted aloha requires some care for stabilization and is essentially essentially limited to throughputs of 1 by E. We will now look at more sophisticated collision resolution techniques that both maintain stability without any complex estimation procedures and also increase the achievable throughput. To get an intuitive idea of how this can be done, note that with relatively small attempt rates, when a collision occurs, it is more likely between only two packets. Thus, if new arrivals could be inhibited from transmission until the collision was resolved, each of the colliding packets could be independently retransmitted in the next slot with probability 1 by 2. This would lead to a successful transmission for one of the packets with probability 1 by 2, and the other could then be transmitted in the following slot. Alternatively, with probability half, another collision or an idle slot occurs. In this case, each of the two packets would again be independently transmitted in the next slot with probability 1 by 2 and so forth until a successful transmission occurred, which would be followed by the transmission of the remaining packet. With this strategy, the two packets require 2 slots with probability half, 3 slots with probability 1 by 4, and I slots with the probability 2 power minus of I minus 1. The expected number of slots for sending these two packets can thus be calculated to be 3, yielding a throughput of 2 by 3 for the period during which the collision is being resolved. There are various ways in which the nodes involved in a collision could choose whether or not to transmit in successive slots. Each node could simply flip an unbiased coin for each choice. Each node could use the arrival time of its collided packet. Assuming a finite set of nodes, each with a unique identifier represented by a string of bits, a node could use the successive bits of its identity to make the successive choice. This way has the advantage of limiting the number of slots required to resolve a collision, since each pair of nodes must differ in at least one bit of their identifiers. All of these alternatives have the common property that the set of colliding nodes is split into subsets, one of which transmits in the next slot. If the collision is not resolved, example, if each colliding node is in same subset, then a further splitting into subsets take place. We call algorithms of this type splitting algorithms. In the subsequent development of these algorithms, we assume a slotted channel, Poisson arrivals, collisions or perfect reception, 0, 1, E, immediate feedback, retransmission of collisions, and an infinite set of nodes. Splitting algorithms tree. Tree algorithms. The first splitting algorithms were algorithms with a tree structure. When a collision occurs, say in the kth slot, all nodes not involved in the collision go into a waiting mode, and all those involved in the collision split into two subsets, example, by each flipping a coin. The first subset transmits in slot k plus 1, and if that slot is idle or successful, the second subset transmits in slot k plus 2. Alternatively, if another collision occurs in slot k plus 1, the first of the two subsets splits again, and the second subset waits for the resolution of that collision. After a collision, all new arrivals wait, and all nodes involved in the collision divide into subsets. Each successive collision in a subset causes that subset to again split into smaller subsets while other nodes wait. The rooted binary tree structure in figure represents a particular pattern of idles, successes, and collisions resulting from such a sequence of splittings. S represents the set of packets in the original collision, and L, left, and R, right, represent the two subsets that S splits into. Similarly, LL and LR represent the two subsets that L splits into after L generates a collision. Each vertex in the tree corresponds to a subset of backlogged packets. Vertices whose subsets contain two or more packets have two upward branches corresponding to the splitting of the subset into two new subsets. Vertices corresponding to subsets with 0 or 1 packet are leaf vertices of the tree. The set of packets corresponding to the root vertex S is transmitted first, and after the transmission of the subset corresponding to any non-leaf vertex, the subset corresponding to the vertex of the left branch and all of its descendant subsets are transmitted before the subsets of the right branch. Given the immediate feedback we have assumed, It should be clear that each node, in principle, can construct this tree as the 0, 1, E feedback occurs. Each node can keep track of its own subset in that tree, and thus each node can determine when to transmit its own backlogged packet. The transmission order above corresponds to that of a stack. When a collision occurs, the subset involved is split and each resulting subset is pushed on the stack. That is, each stack element is a subset of nodes. Then, the subset at the head of the stack, that is, the most recent subset pushed on the stack, is removed from the stack and transmitted. The list from left to right of waiting subsets in the previous figure corresponds to the stack elements starting at the head for the given slot. Note that a node with a backlogged packet can keep track of when to transmit by a counter determining the position of the packet's current subset on the stack. When the packet is involved in a collision, the counter is set to 0 or 1 corresponding to which subset the packet is placed in. When the counter is 0, the packet is transmitted, and if the counter is non-zero, it is incremented by 1 for each collision and decremented by 1 for each success or idle. One problem with this tree algorithm is what to do with the new packet arrivals that come in while a collision is being resolved. A collision resolution period (CRP) is defined to be completed when a success or idle occurs and there are no remaining elements on the stack. At this time, a new CRP starts using the packets that arrived during the previous CRP. In the unlikely event that a great many slots are required in the previous CRP, there will be many new waiting arrivals, and these will collide and continue to collide until the subset gets small enough in this new CRP. The solution to this problem is as follows. At the end of a CRP, the set of nodes with new arrivals is immediately split into J subsets where J is chosen so that the expected number of packets per subset is slightly greater than 1, slightly greater because of the temporary high throughput available after a collision. These new subsets are then placed on the stack and the new CRP starts. The tree algorithm is now essentially completely defined. Each node with a packet involved in the current CRP keeps track of its position in the stack. All the nodes keep track of the number of elements on the stack and the number of slots since the end of the previous CRP. On the completion of that CRP, each node determines the expected number of waiting new arrivals, determines the new number J of subsets, and those nodes with waiting new arrivals randomly chosen one of those J subsets and set their counter for the corresponding stack position. The maximum throughput available with this algorithm optimized over the choice of J as a function of expected number of waiting packets is 0.43 packets per slot. This improvement can be visualized in terms of a stack and implemented by manipulating counters just like the original tree algorithm. Each node must now keep track of an additional binary state variable that takes the value 1 if for some I greater than or equal to 1, the last I slots contained a collision followed by I minus 1 idles. Otherwise, the state variable takes the value 0. If the feedback for the current slot is 0 and the state variable has the value 1, then the state variable maintains the value 1 and the subset on the top of stack is split into two subsets that are pushed onto the stack in place of the original head element. The maximum throughput with this improvement is 0.46 packets per slot. In practice, this improvement has a slight problem in that if an idle slot is incorrectly perceived by the receiver as a collision, the algorithm continues splitting indefinitely, never making further successful transmissions. Thus, in practice, after some number of idle slots followed by splits, the algorithm should be modified simply to transmit the next subset on the stack without first splitting it. If the feedback is very reliable, H can be moderately large, whereas otherwise H should be small. The next improvement in the tree algorithm not only improves throughput but also greatly simplifies the analysis. Consider what happens when a collision is followed by another collision in the tree algorithm. Let X be the number of packets in the first collision and let XL and XR be the number of packets in the resultant subsets. X is equal to XL plus XR. Assume that before knowing that there is a collision, X is a Poisson random variable. Visualize splitting these X packets by coin flip, say, into the two subsets with XL and XR packets respectively before knowing about the collision. Then a priori XL and XR are independent Poisson random variables, each with half of the mean value of X. Given the two collisions, then XL and XR are independent Poisson random variables conditional on XL plus XR greater than or equal to 2 and XL greater than or equal to 2. The second condition implies the first, so the first can be omitted. This means that XR conditional on the feedback is still Poisson with its original unconditional distribution. Variance of the tree algorithm. The tree algorithm requires all nodes to monitor the channel feedback and to keep track of when each collision resolution period ends. This is a disadvantage if the receivers at nodes are turned off when there are no packets to send. One way to avoid this disadvantage while maintaining the other features of the tree algorithm is to have new arrivals simply join the subset of nodes at the head of the stack. Thus, only currently backlogged nodes need to monitor the channel feedback. Algorithms of this type are called unblocked stack algorithms, indicating that new arrivals are not blocked until the end of the current collision resolution period. In contrast, the tree algorithm is often called a blocked stack algorithm. With a tree algorithm, new arrivals are split into a variable number of subsets at the beginning of each collision resolution period, and then subsets are split into two subsets after each collision. With an unblocked stack algorithm, on the other hand, new arrivals are constantly being added to the subset at the head of the stack, and thus collisions involve a somewhat larger number of packets on the average. Because of the relatively large likelihood of 3 or more packets in a collision, higher maximum throughputs can be achieved by splitting collision sets into 3 subsets rather than 2. The maximum throughput thus available for unblocked stack algorithms is 0.40. First come, first serve splitting algorithms. In the second improvement to the tree algorithm we discussed, the second subset involved in a collision is treated as if it had never been transmitted if the first subset contains 2 or more packets. Recall also that a set of colliding packets can be split into 2 subsets in a variety of ways. Example, by coin flipping, by node identities, or by arrival time. For our present purposes, the simplest choice is splitting by arrival time. By using this approach, each subset will consist of all packets that arrived in some given interval, and when a collision occurs, that interval will be split into two smaller intervals. By always transmitting the earlier arriving interval time, the algorithm will always transmit successful packets in the order of their arrival, leading to the name first come, first serve FCFS. At each integer time k, the algorithm specifies the packets to be transmitted in slot k, that is, from k to k plus 1, to be the set of all packets that arrived in some earlier interval, say from t of k to t of k plus alpha of k. This interval is called the allocation interval for slot k. We can visualize the packets arriving after t of k plus alpha of k as being in a queue, and those arriving between t of k and t of k plus alpha of k as being in service. What is peculiar about this queue is that the number of packets in it is unknown, although the nodes all keep track of the allocation interval over which service, that is transmission, is taking place. Figure shows that packets are transmitted in order of arrival. On collisions, the allocation interval generating a collision is split into two sub-intervals, with the leftmost earlier arrivals transmitting first. The FCFS splitting algorithm is the set of rules by which the nodes calculate t of k and alpha of k for each successive k on the basis of the feedback from the previous slot. These rules are simply the improved rules for the tree algorithm discussed previously, specialized to the case where sets of nodes are split in terms of packet arrival times. The previous figure illustrates these rules. When a collision occurs, as in slot k, the allocation interval is split into two equal sub-intervals, and the leftmost, that is, longest waiting, sub-interval L is the allocation interval in slot k plus 1. Thus, t of k plus 1 is equal to t of k, that is, the left boundary is unchanged, and alpha of k plus 1 is equal to alpha of k by 2. When an idle, as in slot k plus 1, follows a collision, the first improvement to the tree algorithm is employed. The previous rightmost interval R is known to contain two or more packets and is immediately split, with RL forming the allocation interval for slot k plus 2. Thus, t of k plus 2 is equal to t of k plus 1 plus alpha of k plus 1, and alpha of k plus 2 is equal to alpha of k plus 1 the whole divided by 2. Finally, successful transmissions occur in slots k plus 2 and k plus 3, completing the CRP. Now, let's consider another example. Figure shown in this screen. In the given example, a collision in slot k is followed by another collision in slot k plus 1. Here, the second improvement to the tree algorithm is employed. Since interval L contains two or more packets, the collision in slot k tells us nothing about interval R, and we would like to regard R as if it never had been part of an allocation interval. As shown for slot k plus 2, this is simplicity itself. The interval L is split, with LL forming the next allocation interval and LR waiting. The algorithm simply forgets R when LL and LR are successfully transmitted slot k plus 2 and k plus 3. The CRP is complete. In the tree algorithm, at the end of a CRP, all the waiting packets split into some number of subsets. Here, since the splitting is being done by allocation intervals in time, it is more appropriate simply to choose a new allocation interval of some given size, say alpha naught. This new interval in slot k plus 4 includes the old interval R that previously lost its identity as a separate interval. In terms of the tree of weighting subsets, the effect of having a right interval lose its identity whenever the corresponding left interval is split is to prune the tree so that it never has more than two leaves. Correspondingly, the stack never remembers more than the top two elements. Whenever the allocation interval corresponds to the left subset of a split, there is a corresponding right subset that might have to be transmitted later. Conversely, when the allocation interval corresponds to a right subset, there are no more waiting intervals. Thus, the nodes in this algorithm need only remember the location of the allocation interval and whether it is a left or right interval. By convention, the initial interval of a CRP is regarded as a right interval. The algorithm gives the allocation interval, that is, T of k and alpha of k, and the status sigma is equal to L or R for a slot k in terms of the feedback, allocation interval, and status from slot k-1. If feedback is equal to E, then T of k is equal to T of k-1, alpha of k is equal to alpha of k-1 the whole divided by 2, sigma of k is equal to L. If the feedback is equal to 1 and sigma of k-1 is equal to L, then T of k is equal to T of k-1 plus alpha of k-1. Alpha of k is equal to alpha of k-1. Sigma of k is equal to R. If feedback is equal to 0 and sigma of k-1 is equal to L, then T of k is equal to T of k-1 plus alpha of k-1. Alpha of k is equal to alpha of k-1 divided by 2. Sigma of k is equal to L. If feedback is equal to 0 or 1 and sigma of k-1 is equal to R, then T of k is equal to T of k-1 plus alpha of k-1. Alpha of k is equal to minimum of alpha naught dot k minus T of k. Sigma of k is equal to R. Analysis of FCFS splitting algorithm. Figure visualizes the evolution of a collision resolution period. The node at the left side of the diagram corresponds to the initial slot of a CRP. The node is split in two as an artifice to visualize the beginning and end of a CRP. If an idle or success occurs, the CRP ends immediately and a new CRP starts on the next slot. Alternatively, if a collision occurs, a transition occurs at node L, I. L indicates the status and 1 indicates that one split in the allocation interval has occurred. Each subsequent idle or collision from a left allocation interval generates one additional split with a smaller left allocation interval, corresponding to a transition in the diagram from L, I to L, I plus 1, where I is the number of times the original allocation interval has been split. A success from a left interval leads to a right interval with no additional split, corresponding to a L, I to R, I transition. A success from a right interval ends the CRP with a transition back to R, 0, whereas a collision causes a new split with a transition from R, I to L, I plus 1. We now analyze a single CRP. Assume that the size of the initial allocation interval is alpha naught. Each splitting of the allocation interval decreases this by a factor of 2 so that nodes L, I and R, I in the diagram correspond to allocation intervals of size 2 power minus I alpha naught. Given our assumption of a Poisson arrival process of rate lambda, the number of packets in the original allocation interval is a Poisson random variable with mean lambda alpha naught. Similarly, there are prior distributions on the numbers of the packets in disjoint subintervals are independent and Poisson. Define Gi as the expected number of packets a prior in an interval that has been split I times. Gi is equal to 2 power minus I lambda alpha naught. We next find the transition probabilities in the figure and show that they constitute a Markov chain. That is, that each transition is independent of the path used to reach the given node. We view the upper half of a node r,0 as the starting state and the lower half as the final state. We start from the left side and work to the right. PR0 is the probability of an idle or success, that is 0 or 1 packet in the first slot. Since the number of packets in the initial allocation interval is Poisson with mean G0, the probability of 0 or 1 packet is PR,0 is equal to 1 plus G0 into e power minus G0. Next, consider the state L,1. This state is entered after collision in state R,0, which occurs with probability 1 minus PR,0. Let XL be the number of packets in the new allocation interval L, that is, the left half of the original interval, and let XR be the number in R, the right half of the original interval. A priori, XL and XR are independent Poisson random variables of mean G1. The condition that L,1 is entered is the condition that XL plus XR greater than or equal to 2. The probability of success PL,1 is thus the probability that XL is equal to 1 and conditional on XL plus XR greater than or equal to 2. Noting that both XL is equal to 1 and XL plus XR greater than or equal to 2 occur if and only if XL is equal to 1 and XR greater than or equal to 1, we have PL,1 is equal to P at XL is equal to 1 into P at XR greater than or equal to 1 divided by P at XL plus XR greater than or equal to 2 is equal to G1 e power minus G1 into 1 minus e power minus G1 divided by 1 minus of 1 plus G0 into e power minus G0. State R,1 is entered if and only if the transaction above takes place, that is, if XL is equal to 1 and XR greater than or equal to 1. Thus, the probability of success PR,1 in state R,1 is the equations shown in this screen. For all I greater than or equal to 1, the equations shown in this screen. Consider state L,2. This can be entered by a collision in state L,1 and idle in L,1 or a collision in R,1. In the first case, interval L is split into LL and LR, and LL becomes the new allocation interval. In the second case and third case, R is split into RL and R with RL becomes the new allocation interval. For the first case, let XLL and XLR be the number of packets in LL and LR respectively. A priori, these are independent Poisson random variables of mean G2 each. The collision from L,1 means that XL plus XR greater than or equal to 2 and XL greater than or equal to 2 which is equivalent to the single condition XL greater than or equal to 2. Consider the second case, that of an idle in L, 1. This means that XL plus XR greater than or equal to 2 and XL is equal to 0, which is equivalent to XR greater than or equal to 2 and XL is equal to 0. PL, 2 in this case is the probability that RL, the left half of R, contains one packet given that R contains at least 2. Finally, for the case of a collision in R, 1, we have XL plus XR greater than or equal to 2, XL is equal to 1 and XR greater than or equal to 2, or equivalently XL is equal to 1, XR greater than or equal to 2. Thus, the Markov condition is satisfied for L, 2. Generally, no matter how L, 2 is entered, the given interval L or R preceding L, 2 is an interval of size alpha naught by 2 of a Poisson process conditional on the given interval containing 2 or more packets. If a success occurs on the left half, the number of packets in the right half is Poisson conditional on being 1 or more, yielding the expression for PR, 2. This argument repeats for I is equal to 3, 4, so on. The discussed is a Markov chain and the three equations give the transition probabilities. The analysis of this chain is particularly simple since no state can be entered more than once before the return to R, 0. The probabilities PL, I and PR, I that L, I and R, I respectively are entered before returning to R, 0 can be calculated iteratively from the initial state R, 0. The equations shown in this screen. Let K be the number of slots in a CRP, thus K is the number of states visited in the chain including the initial state R, 0 before the return to R, 0. E of K is equal to 1 plus sigma I is equal to 1 to infinity of P of L, I plus P of R, I. We must also evaluate the change in T of K for one CRP to the next. For the assumed initial interval of size alpha naught, this change is at most alpha naught, but if left-hand intervals have collisions, the corresponding right-hand intervals are returned to the waiting interval and the change is less than alpha naught. Let f be the fraction of alpha naught returned in this way over a CRP so that alpha naught of 1 minus f is the change in T of K. The probability of a collision in state L, I is the probability that the left half interval in state L, I contains at least 2 packets given that the right and left intervals together contain at least 2, that is, the equations shown in this screen. The fraction of the original interval returned on such collision is 2 power minus I, so the expected value of f is the equations shown in this screen. Figure plots comparison of expected delay for stabilized slot Aloha and the FCFS splitting algorithm as a function of arrival rate. One becomes unbounded as the arrival rate approaches 1 by t and the other as the arrival rate approaches 0.4871. Improvements in the FCFS splitting algorithm. Splitting intervals into equal-sized sub-intervals is slightly non-optimal in achieving maximum stable throughput. When each interval is split into the optimally sized sub-intervals, the maximum stable throughput increases to 0.4878. Another improvement of 3.6 into 10 power minus 7 results if in state r, I for large I, sum of the waiting interval is appended to the right side interval. While these improvements are not significant practically, they are of theoretical interest in determining optimality in terms of maximum stable throughput. The maximum stable throughput achievable by an algorithm lies somewhere between 0.4878 and 0.587. For any finite set of M nodes, we have seen that TDM can trivially achieve any throughput up to 1 packet per slot. This striking difference between finite and infinite M seems paradoxical until we recognize that with TDM, expected delay for a given lambda increases linearly with M, whereas the algorithm that assume M is equal to infinity achieve a delay bounded independently of M. Round-robin splitting. A final variation of the FCFS splitting algorithm can be applied if there is an identifiable finite collection of nodes numbered 1 to m. Consider the nodes to be arranged conceptually in a circle with node I plus 1 following I, 1 less than or equal to I less than m, and node 1 following m. Rather than forming allocation sets in terms of packet arrival times, an allocation set consists of a contiguous set of nodes, say I to j, around the circle. After completion of a CRP, the algorithm then allocates the next successive set of nodes around the circle. The size of allocation sets initiating CRPs varies with the time to pass around the circle, so that under light loading, an initial allocation set would contain all nodes, whereas under heavy loading, initial allocation sets would shrink to single nodes, which is equivalent to TDM. Stability in slotted Aloha pseudo-Bayesian algorithm. One simple approach to achieving stability should be almost obvious now. The p-success is approximately g of n e power minus g of n, which is maximized at g of n is equal to 1. Thus, it is desirable to change QR dynamically to maintain the attempt rate g of n at 1. The difficulty here is that n is unknown to the nodes and can only be estimated from the feedback. There are many strategies for estimating n or the appropriate value of QR, example HAL82 and IRIV85. All of them in essence increase QR when an idle slot occurs and decrease QR when a collision occurs. Stability and maximum throughput. Given the no buffering assumption, the system has a well-defined steady-state behavior for all arrival rates. With the infinite node assumption, on the other hand, there is no steady-state distribution and the expected delay grows without bound as the system continues to run. With the no buffering assumption, the system discards large number of arriving packets and has a very large but finite delay, whereas with infinite node assumption, no arrivals are discarded but the delay becomes infinite. We shall use the infinite node assumption and define a multi-axis system as stable for a given arrival rate if the expected delay per packet, either as a time average or an ensemble average in the limit of increasing time, is finite. Ordinary slotted Aloha is unstable in this sense for any arrival rate greater than 0. Note that if a system is stable, then for a sufficiently large but finite number of nodes m, the system, regarding each arrival as corresponding to a new virtual node has a smaller expected delay than TDM, since the delay of TDM for a fixed overall arrival rate increases linearly with M. The maximum stable throughput of a multi-axis system is defined as the least upper bound of arrival rates for which the system is stable. For example, the maximum stable throughput of ordinary slotted Aloha is 0. Our purpose with these definitions is to study multi-axis algorithms that do not require knowledge of the number of nodes M and that maintain small delay for given lambda independent of M. When the estimate of backlog is perfect and g of n is maintained at the optimal value of 1, then, according to the Poisson approximation, idles occur with probability 1 by e approximately equal to 0.368, successes occur with probability 1 by e, and collisions occur with probability 1 minus 2 by e approximately equal to 0.264. Thus, the rule of changing QR should allow fewer collisions than idles. The maximum stable throughput of such a system is at most 1 by e. When the backlog is large, the Poisson approximation becomes more accurate. The successes rate is then limited to 1 by e, and thus the drift is positive for lambda greater than 1 by e. If nodes use both their own history of retransmissions and the feedback history in their decisions about transmitting, maximum stable throughputs considerably higher than 1 by e are possible. Pseudo-Bayesian algorithm. Rivest's pseudo-Bayesian algorithm RIV85 is a particularly simple and effective way to stabilize Aloha. This algorithm is essentially the same as an earlier independently derived algorithm by Mikhail Lov, MiG-79, but Rivest's Bayesian interpretation simplifies understanding. It differs from slotted Aloha. New arrivals are regarded as backlogged immediately on arrival, rather than being transmitted with certainty in the next slot. They are transmitted with probability QR in the same way as packets involved in previous collisions. Thus, if there are n backlogged packets, including new arrivals, at the beginning of a slot, the attempt rate is g of n is equal to nqr, and probability of a successful transmission is nqr into 1 minus qr the whole power n minus 1. For unstabilized Aloha, this modification would not make much sense, since QR has to be relatively small and new arrivals would be unnecessarily delayed. For stabilized Aloha, however, QR can be as large as 1 when the estimated backlog is negligible, so that new arrivals are held up only when the system is already estimated to be congested. This modification increases the probability of success if the backlog estimate is accurate. The algorithm operates by maintaining an estimate CC of the backlog n at the beginning of each slot. Each backlogged packet is then transmitted independently with probability QR of n cap is equal to minimum of 1, 1 by n cap. The minimum operation limits QR to at most 1, and subject to this limitation tries to achieve an attempt rate g is equal to nqr of 1. For each k, the estimated backlog at the beginning of slot k plus 1 is updated from the estimated backlog and feedback for slot k according to the rule n cap of k plus 1 is equal to max of lambda into n cap k plus lambda minus 1. For idle or success, n cap k plus lambda plus e minus 2 the whole power minus 1 for collision. The addition of A to the previous backlog accounts for new arrivals, and the maximum operation ensures that the estimate is never less than the contribution from new arrivals. On successful transmissions, 1 is subtracted from the previous backlog to account for the successful departure. Finally, subtracting 1 from the previous backlog on idle slots and adding e minus 2 the whole power minus 1 on collisions has the effect of decreasing n cap when too many idles occur and increasing n cap when too many collisions occur. For large backlogs, if n cap is equal to n, each of the n backlogged packets is independently transmitted in a slot with probability QR equal to 1 by n. Thus, g of n is 1, and by the Poisson approximation, idles occur with probability 1 by e and collisions with probability e minus 2 by e, so that the decreasing n cap by 1 on idles and increasing n cap by e minus 2 the whole power minus 1 on collisions maintains the balance between n and n cap on the average. If the probability distribution of nk is Poisson with parameter n cap k greater than or equal to 1, then given an idle or successful transmission in slot k, the probability distribution of nk plus 1 is Poisson with parameter n cap k plus lambda minus 1. Given a collision, the resulting distribution of nk plus 1 is not quite Poisson but is reasonably approximated as Poisson with parameter n cap k plus 1. For this reason, the algorithm is called pseudo-Bayesian. Figure shows the drift of n and n minus n cap for the pseudo-Bayesian stabilization algorithm. When the absolute value of n minus n cap is large, it approaches 0 faster than n increases. It provides some heuristic understanding of why the algorithm is stable for all lambda less than 1 by e. The state of the system is characterized by n and n cap, and the figure shows the expected drift in these variables from one slot to the next. If n and n cap are large and equal, the expected drift of each is lambda minus 1 by e, which is negative. On the other hand, if the absolute value of n minus n cap is large, the expected drift of n is positive, but the expected reduction in n minus n cap modulus is considerably larger. Thus, if the system starts at some arbitrary point in the n, n cap plane, n might increase on the average for a number of slots, but eventually n and n cap will come closer together and then n will decrease on the average. In applications, the arrival rate lambda is typically unknown and slowly varying. Thus, the algorithm must either estimate lambda from the time average rate of successful transmissions or set its value within the algorithm to some fixed value. It has been shown by Mikhailov and Tsitsiklis that if the fixed value 1 by e is used within the algorithm, stability is achieved for all actual lambda less than 1 by e. Nothing has been proven about the behavior of the algorithm when a dynamic estimate of lambda is used within the algorithm. Approximate delay analysis. An exact analysis of expected delay for this algorithm, even with known lambda, appears to be very difficult, but it is instructive to analyze an approximate model. Assume that lambda is known and that the probability of successful transmission P success is 1 by E whenever the backlog N is 2 or more, and that P success is equal to 1 for N is equal to I. This is a reasonable model for very small lambda, since very few collisions occur and QR is typically 1. It is also reasonable for large lambda less than 1 by E, since typically N is large and N cap approximately equal to N. Let Wi be the delay from the arrival of the ith packet until the beginning of the ith successful transmission. If the system were first come and first served, Wi would be the queuing time of the ith arrival. The average of Wi over all I is equal to the expected queuing delay W. Let Ni be the number of backlogged packets at the instant before I's arrival. Ni does not include any packet currently being successfully transmitted, but does include current unsuccessful transmissions. Wi can be expressed as Wi is equal to Ri plus sigma j is equal to 1 to Ni Tj plus Yi. Ri is the residual time to the beginning of the next slot, and T1 for Ni greater than 0 is the subsequent interval until the next successful transmission is completed. Similarly, Tj1 less than j less than or equal to Ni is the interval from the end of the j minus 1th subsequent success to the end of the jth subsequent success. For those Ni successes, Yi is the remaining interval until the beginning of the next successful transmission, that is, the ith transmission overall. Observe that for each interval Ti, the backlog is at least 2, counting the new ith arrival and the Ni packets already backlogged. Thus, each slot is successful with probability 1 by E, and the expected value of each Ti is E. Next, observe that Little's formula relates the expected values of Wi and Ni, that is, Wi is the weight not counting the successful transmission, and Ni is the number in the system not counting successful transmissions in process. Finally, the expected value of Ri is 1 by 2 counting time in slots. Thus, W is equal to half plus lambda EW plus E of Y. Now, consider the system at the first slot boundary at which both the I minus first departure and the ith arrival has occurred. If the backlog is 1 at that point, that is, only the ith packet is in the system, then Yi is 0. Alternatively, if n greater than I, then E of Yi is equal to E minus 1. Let Pn be the steady state probability that the backlog is n at a slot boundary. Then, since a packet is always successfully transmitted if the state is 1 at the beginning of the slot, we see that P1 is the fraction of slots in which the state is 1 and a packet is successfully transmitted. Since lambda is the total fraction of slots with successful transmissions, P1 by lambda is the fraction of packets transmitted from state 1, and 1 minus P1 by lambda is the fraction transmitted from higher numbered states. It follows that E of Y is equal to E minus 1 into lambda minus P1 by lambda. Finally, we must determine P1. Lambda is equal to P1 plus 1 minus P0 minus P1 the whole divided by E. State 0 can be entered at a slot boundary only if no arrivals occurred in the previous slot and the previous state was 0 or 1. Thus, P0 is equal to P0 plus P1 e power minus lambda. Solving for P1 gives P1 is equal to 1 minus lambda into e power lambda minus 1 divided by 1 minus of e minus 1 into e power lambda minus 1. Combining the previous equations, we get W is equal to e minus half divided by 1 minus lambda e minus of e power lambda minus 1 into e minus 1 the whole divided by lambda into 1 minus of e minus 1 into e power lambda minus 1. This value of W is quite close to delay values for the pseudo-Bayesian algorithm obtained through simulation. Figure shows comparison of expected waiting time W in slots from arrival until beginning of successful transmission for stabilized Aloha and for TDM with m is equal to 8 and m is equal to 16. For small arrival rates, the delay of stabilized Aloha is very little more than waiting for the next slot, whereas the arrival rate approaches 1 by e, the delay becomes unbound. Figure plots E of W for this approximate model and with the queuing delay for TDM with 8 and 16 nodes. It is quite surprising that the delay is so small even for arrival rates relatively close to 1 by e. It appears that the assumption of immediate feedback is unnecessary for stabilization strategies of this type to be stable. The argument is that feedback delay will make the estimate n cap less accurate, but n by n cap will stay close to 1 for large n. Binary exponential backoff. In the packet radio networks and in some other multi-access situations, the assumptions of 0, 1, e feedback on all slots is unrealistic. In some other systems, a node receives feedback only about whether or not its own packets were successfully transmitted. It receives no feedback about slots in which it does not transmit. Such limited feedback is sufficient for slotted Aloha but is insufficient for the backlog estimation of the pseudo-Bayesian strategy. Binary exponential backoff is a stabilization strategy used in Ethernet that employs only this small limited form of feedback. This strategy is very simple. If a packet has been transmitted unsuccessfully I times, then the probability of transmission in successive slots is set at QR is equal to 2 power minus I or is uniformly distributed over the next 2 power I slots after the ith failure. When a packet initially arrives in the system, it is transmitted immediately in the next slot. Some rationale for this strategy can be seen by noting that when a packet first arrives with this limited feedback, the node knows nothing of the backlog, so the immediate first transmission is reasonable. With successive collisions, any reasonable estimate of backlog would increase, motivating the decrease in the local QR. To make matters worse, however, as QR is reduced, the node gets less feedback per slot about the backlog, and thus, to play safe, it is reasonable to increase the backlog estimate by larger and larger amounts on each successive collision. Unfortunately, in the limit as the number of nodes approaches infinity, this strategy is unstable for every arrival rate greater than 0. It is unknown whether or not any strategy can achieve stability with this type of limited feedback. Conclusion. In this chapter, we have covered the following in detail: review of ALOHS and CSMA, stability in slotted ALOHA, pseudo-Bayesian algorithm, splitting algorithms, tree and first come first serve FCFS splitting,